it's important to understand which version of the chain rule. There's like 5 different versions, at least here. But it all comes down to understanding the partial derivatives that you want to calculate, or the derivatives that you want to calculate, and then drawing a simple diagram of x. So w depends on x, so I draw a little link. And then x depends on 2 variables, r and s. So I make a little branch, I guess, a splitting branch to show that x is dependent on 2 things. Now, how do I actually get a chain rule out of that? Now, back to the diagram, okay? Let's say I wanted to calculate dw dr. I look at all the paths from the top down to r. And when I move from letter to letter, I form a derivative. So I can go dw dr df dx times dx dr. That's it. df dx times dx dr. If that's really getting on your nerves at the back, feel free to come down the front. You know, if it's really annoying, just come on down. Okay, so when I move from letter to letter, I form a derivative. Now, who can tell me why is this a regular derivative and why is this a partial derivative? Why aren't they both partials, or why aren't they both just regular derivatives? Anyone? Anyone? Yes, up the back, yes. Correct. Yes, very good. In this setup, f depends on 1 variable, so these things make sense, and x depends on 2 variables. Very good. Okay, so to get dw ds, go down the paths leading to an s. So it would be df dx times dx ds. That would be this chain rule. So just draw these simple diagrams, and they're all sorted. So let me show you how it works for a specific example. And I think this is actually in your tutorial sheets. So what I'm going to do is let x be S on R. So this is my setup. All right, now to derive the chain rule, we just show the dependence, sorry, hang on, F. Sorry, beg your pardon. So we just draw our little tree diagram. F depends on 1 variable, x. X depends on 2 things, R and S. And then to form the actual chain rule that we're going to use, we want dw dr in this case. Go down all the paths leading to an R. And when you go from letter to letter, form a derivative. Okay. So now let's actually compute some of these derivatives in our chain rule. df dx is going to be something like 1 on 1 plus x squared, because we're differentiating inverse tan, right? And dx dr is going to be something like, holding the s fixed, it's going to be something like minus s on r squared. So now you have a choice. Which variables do I want the final answer in? Well, in this case, I'm going to do it in terms of r and s because the variable appears in the derivative, dw dr. So I can go and back substitute. And then all I need to do is just solve this, well, I guess simplify this, and you can get down to the following. All right, just a little bit of algebra. So that's a pretty standard example, something you might see on a class test. Fairly straightforward. So that's one of the simplest kinds of chain rules that you'll come across. Yes? Correct. So x is like an intermediate variable. Okay, you can think of x as an intermediate variable. Yep. Any other questions? Very standard example. All right, So here, the situation gets a little bit more complex. F depends on two things, x and y, and each of those variables depend on t. So the chain rule starts to get a little bit more complicated now. But again, if you just draw the simple diagram that I just showed you, it's very easy to derive. Okay? So if I wanted to form the chain rule, I note that F depends on two things, x and y, and each of these depend on t. Okay? So all I do is to get df dt or dw dt, whatever you want to call it, I work down both columns because they both lead to a t. All right, so it's df dx times dx dt plus the other column, df dy times dy dt. Oops, sorry. Oh, it's so boring. Now, what's wrong with the way I've written the chain rule down there? What's wrong with this line? It should be partials there and there. Okay? Okay, so let's do an example involving that version of the chain rule. Now, bear with me for this example because you may look at this example and go, well, the method that you're teaching me on this example is just wrong. I agree with you. If I really wanted to find df dt, what I would do in practice here is substitute in for x, substitute in for y, and then just take the derivative. Okay? But there are cases where you cannot do that, and the following example is actually a case of that. So let's just do this using the chain rule and see how we go. So, f depends on two variables, x and y, and each of those depend on t. Our chain rule will be the following. All right, df dx times dx dt plus df dy times dy dt. So all I need to do in this example is calculate these four derivatives and then simplify. Okay? That's all we're doing here. Now, yes, I know you can just plug these in and differentiate. I would do the same thing, but we're setting ourselves up for the next example here. So df dx, what's that going to be? It's going to be 2xy squared. Dx dt is going to be minus the sine t. Df dy is going to be 2y x squared. And dy dt is going to be cos t. So now all I need to do is simplify, get everything in terms of the same variables. So what I'm going to do is substitute in here for x and y. So if we multiply through by that, we're going to have minus sine cubed t. Now, there's a few things that are a bit unsettling about that method of solution. Firstly, we actually did a substitution in that bottom line. So why didn't we just substitute in at the start and just differentiate with respect to t? That would be the normal and logical thing to do. Well, the next example is an example where you cannot do that simpler kind of approach. So let me show you. Let me show you. In this example, we've got the ideal gas equation. Now, it relates the pressure, volume, and temperature of a mole of an ideal gas. And Here, P's the pressure in kilopascals, V's the volume in litres, and big T is the temperature in degrees Kelvin. What we're asked to do is find the rate at which the pressure is changing with respect to time at this instant. Now you'll see there's a couple of values here and a couple of derivatives. In particular, derivatives with respect to time. So we can conclude that big T and big V depend on time. Okay, let's say T is in seconds. Okay, so the first thing we need is our chain rule. So again, I'm just going to note that P depends on two things, temperature and volume, and both of those depend on time. Okay, so all I need to do to calculate dP d little t is just go down the branches, form a derivative when I move from letter to letter. Okay, so it's going to be the following. dP d big T times d big T d little t. Plus the other branch, dP dV times dV d little t. That's an ordinary derivative there. Okay, so let's take some derivatives and simplify. We can simplify this and this. So if we go back to our original equation and differentiate to find the partials, we're going to get 8.31 on big V. Now, we don't know what this is in general, so I just got to leave it. This partial will be minus 8.31 big T on V squared. We don't know what this is in general. So that's the general setup. But what we're asked to do with this question is to calculate this derivative at a particular instant, a particular point in time. Okay, so what we need to do is just make some substitutions and simplify if we can. So at our instant of interest, we substitute these values into here. So just subbing in, okay, so now it's just a matter of simplifying. If you simplify this, you'll get something like the following. Okay, now remember, in your class test, you won't necessarily have you won't have a calculator. So it's important to, deal with this. There's a quick way to deal with this mentally, but I'm just going to write down the answer. Okay, so that is a good example of what you might see possibly in a class test, possibly as a sub-question on the end semester exam. Okay. So that's a good example. You cannot solve this example by the method that I suggested in the previous example. You can't just make a substitution straight up. Yes? Yes? Oh, sorry. Yes, you're right. It should be, what am I doing? How's that? Better? Thank you. All right. Now, like I said before, the chain rule can get kind of messy, kind of complicated. In this example, you've got W depending on X and Y, and both of those variables depend on two other variables. But you can easily get the chain rule for this just by drawing a picture again. All right, so F depends on X and Y, and both of those depend on R and S. So to get the chain rule, just work your way from the top down to, say, R. There's two ways to get there, and you'll get one chain rule. Work your way down the branches to an S, and you'll get the other chain rule. Okay? It's pretty simple, and it easily generalizes. All right, so here's a good example that has been in previous class tests. Suppose we've got a function, f. We don't really know what f is, but we know it's got this kind of dependency. What we're asked to do is show that functions of this type satisfy a special equation known as a partial differential equation. Okay? Now we learnt last time that partial differential equations are important for modelling in engineering, applied math, physics, just about everywhere. What we're trying to do here is show that functions of this form satisfy a partial derivative. So what I'm going to do is use the chain rule here to calculate this derivative and this derivative. And then I'm going to show that the equation holds, or the equation balances. So, I'm going to introduce these intermediate variables, just to keep things simple. Let's draw our diagram, and then we can formulate our chain rule. F, in this case, f will depend on x and y. Oops. And x depends on u and v, and y depends on u and v. So, to calculate our chain rules, all I need to do for this one is to go down the branches that lead to a u. So df dx times dx du plus df dy times dy du. Now I'm going to write this in terms of subscripts, just to keep it a bit simple. So what I can do now is see if I can simplify this expression. Now I don't know what f is. That's the frustrating part. I don't know what f is, so I can't really differentiate it. But I do know what x and y are. So x sub u, what's that going to be? 1. Y sub u, dy du, is going to be minus 1. Okay, that's as far as I can take that, because I don't know what f is, so I can't differentiate it. Okay? What about the other chain rule? dz dv. Well, let's work our way down through the branches to v's. So let's see if I could simplify here. X sub v is going to be minus 1. Y sub v is going to be 1. So what I'm going to do is take these two expressions, sub them into the left-hand side, and see if they all cancel out. If that's true, then the equation will hold, and solutions, there will be a solution, well, I guess functions of this type will be a solution to this equation. So let's call this star. So let's substitute in. And, well, they're going to cancel out. Oh my God. So we're absolutely delighted. We're really happy. Okay? Well, let me move that over. Okay, so we don't know what f is, but we know that if it has a certain structure, it'll satisfy that partial differential equation. I was wondering where you went. I was wondering. I was kind of missing you in a bizarre way. Yeah. Okay. All right, now it's getting really complicated. F depended on 3 variables, and each of those depend on 1 variable. Now we're getting to like the extreme end of things now, so don't worry if it's a little bit abstract. But, you know, I don't care. I can derive any chain rule, right? That's it. I can derive any chain rule just from a picture. Easy. Okay? Just work your way down to the t's. Go down each branch. When you go from letter to letter, form a derivative and add everything together. That's it. That's it. Okay? All right, so here's an example that I've created earlier. In this case, you have a function of 3 variables, x, y, and z. And each of those variables, each of those variables depend on t. Now, in the next slide, you can kind of see what the domain of this function w looks like. It's known as a helix. So you can think of it as a spring. Okay? For this setup, we're asked to calculate dw dt, and what is the value of that derivative at t equals 0. So you apply the chain rule, go through, calculate the individual derivatives, simplify, and you'll get your answer. Okay? But that is right on the extreme end of problems for the chain rule. All right. Again, looks complicated, but it's not. You can get this chain rule just by drawing the picture. Very simple. So here's another example. Again, one that I've created earlier. Here we've got a function of 3 variables, x, y, and z. Each of those depend on 2 variables. Go through, formulate your chain rule, work out your derivatives. All right, so let's look at a pseudo application. How can you use these things in, for example, modelling? All right, the partial differential equation, 6, is known as a special equation called the advection equation. Now, here a is just a constant. Use a function of 2 variables. You can think of x as representing position and t as representing time. Okay? We're asked to use the chain rule to show that a solution to this PDE, the advection PDE, is of this form where f is a differentiable function. Okay? Now, just to give you some sort of insight into that, with advection, you can think of it as representing the transport of salt that's dumped in a river. Okay, if the river is originally fresh water and is flowing quickly, the predominant form of transport of the salt in the water will be advective. So you can think of U as representing the concentration of salt in a river at time t at position x. So how far x would represent, position or how far you go down the river. Okay, so let's solve this and use our chain rule somehow. All right, so under this relationship here, f depends. Oh, sorry. Let's make an independent, a intermediate variable. So I'm going to say let v equal x minus at. Okay, a is a constant, x and t are your variables, right? So to set up the chain rule, I notice that f depends on v, and v depends on two things, x and t. Remember, a is a constant. We don't know what it is, but it's just a constant. So to set up our chain rule, we just work from the top to the bottom. All right, so our chain rules are the following. Basically, you want to calculate this derivative and this derivative. So du dx, that's going to be df dv times dv dx. All right, so I don't know what f is, but I can calculate this dv dx. It's going to be 1. What about du dt? Well, that's going to be df dv times dv dt. Again, I can't calculate this, but I can calculate this. dv dt is going to be negative a. So what I do now is just put those two derivatives into my advection, the left-hand side of my advection equation, and see if they cancel everything out. All right, so it's going to be a times du dx, which is this, plus this. And if you look closely, they'll just cancel each other off. And the equation holds. So there must be a, I guess a solution is of this form. Question? What, sorry? I can't hear. Okay. So, that is the chain rule. That is the chain rule. It's important to understand which version of the chain rule. There's like 5 different versions, at least here. But it all comes down to understanding the partial derivatives that you want to calculate, or the derivatives that you want to calculate, and then drawing a simple diagram.